Now, let us classify crystalline solids. Crystalline solids can be classified into four different categories depending upon the type of constituent particles and the nature of attractive forces operating between them. They are: first one, molecular solids; second one, ionic solids; third one, covalent or network solids; and the last one, metallic solids. Firstly, let us take up molecular solids. In molecular solids, the constituent particles are molecules. Depending upon the nature of molecules, these solids are further classified into three types: nonpolar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. What are nonpolar molecular solids? In nonpolar molecular solids, the constituent particles are either atoms like noble gases such as helium, neon, argon, etc., or nonpolar molecules like H2, Cl2, I2, CH4, etc. Generally, they are liquids or gases at room temperature and they exist as solids at supercooled temperature. In these solids, the electron cloud is symmetrically distributed and the molecules does not have any polarity. Sometimes these atoms and nonpolar molecules lose their symmetry in electron cloud distribution for a shorter time and produce instantaneous dipole. These dipoles distort the electron cloud of the neighboring atom or nonpolar molecule, including dipole moment in them. Now, electrostatic force of attraction between these instantaneous dipoles are called as dispersion forces or London forces. Due to the presence of weak forces, these solids have low melting point and boiling point. Let us study about polar molecular solids. In polar molecular solids, the constituent particles are polar molecules like HCl, SO2, etc. The molecules of these solids are held together by dipole-dipole forces of attraction. Due to the presence of dipole-dipole interactions, these solids are soft and their melting and boiling points are comparatively higher than those of nonpolar solids. But still, as these solids do not have very high melting and boiling points, they exist as gases or liquids at room temperature under ordinary pressure. Now, let us study about hydrogen bonded molecular solids. In hydrogen bonded molecular solids, the constituent particles are molecules which contain hydrogen atom linked to highly electronegative atom such as fluorine, oxygen, or nitrogen of neighboring molecule. This link between hydrogen atom and highly electronegative atom of its neighboring molecule is known as hydrogen bond, and the hydrogen bond is represented as dotted lines. Due to the presence of strong hydrogen bonds, these solids have higher boiling and melting point when compared to nonpolar and polar solids. These solids are poor conductor of electricity and they exist as volatile liquids or soft solids at room temperature and pressure. Let us consider metallic solids. In metallic solids, the constituent particles are metal ions and free electrons. Metals have a tendency to lose electrons and becomes positively charged ions. These group of positively charged metal ions are called as kernels, and the electrons can easily flow throughout the metal crystal like water in the sea. These mobile electrons are attracted by the positively charged ions and holds these ions together. The attractive force that holds the kernels and the mobile electrons in the metallic solid is called as metallic bond. Due to the presence of strong metallic bonds, the metallic solids have high melting points and boiling points. The free electrons in these solids are responsible for high electrical and thermal conductivities of metals. In fact, the color of certain metals are also due to the presence of these free electrons. Some of the examples of metallic solids are copper, iron, aluminium, silver, etc. Let us discuss about ionic solids. In ionic solids, ions are the constituent particles. In these solids, there is a three-dimensional arrangement of cations and anions that are held together by strong electrostatic force of attraction. As a result, these ions are not free to move and are closely packed, and hence these are hard and brittle solids. Ionic solids possess high melting and boiling points. Being ionic in nature, these solids are soluble in polar solvents like water, but insoluble in nonpolar solvents like ether. Ionic solids act as insulators in solid state, but in aqueous solutions or in molten state, they act as a very good conductor of electricity. Here, the question is, why are ionic solids very good conductors in the molten state and not in the solid state? In ionic solids, the electrical conductivity is due to the movement of the ions. However, in the solid state, the ions are in fixed positions and they are not free to move. However, in molten state or aqueous solutions, the individual ions are free to move. And when potential difference is applied, these ions act as a charge carriers and become good conductors of electricity. Some of the examples of ionic solids are sodium chloride, zinc sulfide, magnesium oxide, cesium chloride, etc. Now, let us discuss about covalent solids. These are crystalline solids in which the constituent particles are non-metal atoms linked to adjacent atoms by covalent bonds throughout the crystal structure. As a result, network of covalent bonds are formed. Due to large network of covalent bonds, these solids are also known as network solids. These solids are very hard and brittle and have extremely high melting and boiling points. These covalent solids, due to the absence of free ions, act as bad conductor of electricity. One of the most common examples of covalent or network solid is diamond, where each carbon atoms are linked together by 4 covalent bonds to give a three-dimensional structure. However, there is one exception whose properties are quite different from the other covalent solids. Let us study about that exception. And the exception is graphite. Though it is a covalent solid, unlike other covalent solids, it is soft and good conductor of electricity. This exceptional behavior of graphite is due to its typical layer structure. In graphite, carbon atoms are arranged in different layers. We know that carbon is tetravalent in nature and has 4 valence electrons. In each layer, one carbon atom is bonded to 3 other neighboring atoms within the same layer. The unbounded 4th valence electron of each carbon atom remains unbounded and is present between the layers. This fourth valence electron is free to move within the structure. When potential difference is applied, these free electrons act as a charge carriers and makes graphite a good conductor of electricity. The force of attraction between each layer of graphite is very weak. Due to this, different layers can easily slide over the one another. This makes graphite soft and good solid lubricant. Best examples of covalent solids are diamond, silicon carbide, silica, etc.